Hi, in this video, we're going to take a look at supervised learning with some regression models. Okay, so remember, supervised learning is a situation where I have a target variable. I want to predict a particular variable, one particular variable, or I want to understand the relationship between predictor variables and a target variable, that one target variable. All right, so regression is a situation where I have a numeric target variable. So I have a number of some form. So this is very different from win or lose. That's a classification. Or something like yes, no, that's a classification. Red, yellow, green, that could be a classification if these are target variables. So like example of a classification problem could be has COVID-19, yes or no. A regression problem would be how extreme is the infection in some form of measurement of pathogens per milliliter of blood. Something like pathogens per milliliter of blood would be an example of a numeric value. So that would be a regression target, while infected yes or no would be a classification problem. Okay, so to take a look at this, we're not going to do anything as risque as COVID-19. Thank goodness, I want to keep away from it. We're going to work with Halloween candy because that's way more fun. We're going to once again look at the ultimate Halloween candy power ranking. And the data set's taken from Kaggle, and we have a bunch of predictor variables. And in this data set, what it does, it takes candy A, candy B, and the person votes which one's better. Candy A, candy B, different A's and B's, which one's better? New candy A, new candy B, which one's better? And the target variable is what % of the time does a candy win, and the predictors are the features of the candy. Okay, so what we really want to do here is we want to go ahead, do some machine learning. We're going to load the data, say what X and Y are. So X is the collection of predictor variables, Y is the winning percentage. Then we're going to do train test split. And then we're going to go through and look at different models. Now I'm doing train test split instead of cross-validation for no particular reason. I just chose to do it. So let's go ahead and get some packages loaded in. Seaborn, Matplotlib, NumPy, Pandas. All right, so now let's get our candy data. It's a CSV file, and I've posted this in Canvas already. Now let's get X and Y. So let's take a look at X. So we can just see that, we have a bunch of numbers, nice, it's beautiful, it's beautiful. And Y, once again, a bunch of numbers, but here this array has just one vector, while the previous one had a whole bunch of different columns of data. Because we had a whole bunch of predictor variables, we had chocolate, we had fruity, we have caramel, we had peanutty, almondy, nougat, crisp rice, and so on. Now what we want to do the train test split. We want to break up the data into a training set and a test set. Remember, the training set is the set I build my data on. The test set gives me information about how well I can expect the data to perform in the future. So we're going to get training statistics and test statistics. Training statistics tell me how well the model fits on the data, and test statistics indicates to me, it doesn't actually tell me, but it indicates how well the model will perform in the future on the population. So we don't actually care about the sample at all. We only care about the population. I'm just using the sample to reach the population. Remember, if I knew what was going on, I wouldn't be doing data science. So everything is just kind of like an estimate. We don't actually know what's going to work. Just our best guess. So let's get train test split, get some metrics going. And I'm going to do a train test split. I went ahead and said that my train size was 60% and my test size was 40%. I like 50-50, but the reason why I split 60-40 is to make sure I had different dimensions. That way, while I was coding, if I accidentally switch test and train, try to put them, X train and Y test together, they'd have different dimensions and the computer would spit an error at me. All right, so the first one we want to look at vanilla regression. We've already talked about regression up, down, left, and right. I'm just going to run through it. This is the one where I'm trying to minimize the sum of squares of the error. So prediction minus observed, square it, add them all up. And I'm trying to minimize the sum of squared error with this. Okay, so let's go through. And we're pulling in a linear model from sklearn. I'm defining reg as linear regression. Let's fit the model using the training data. Now we're going to make our predictions on the training and the test data. Now let's go ahead and calculate the mean absolute error. Okay, so mean absolute error. So remember, when a moment ago I said minimize the sum of squares error. Well, this is a little bit different. What we're doing, we're going to take the prediction minus the true value, subtract absolute value, then take the average of the absolute values. This is a little bit different than what we were doing for minimizing the sum of squared error. Sum of squares error takes prediction, true value, subtracts, then squares it. Squaring makes it positive, then they add it up. And adding up is very close to taking an average because it's just, you're just short of division. All right, so let's go ahead and take a look. All right, so why do I like mean absolute error? Mean absolute error is easier to interpret. All right, so the average difference between my observed and the true value, my observed and the predicted value, is about 7.5 on the training set. That's easier to interpret. If I had that squaring going on, it would be hard for me to tell, like, what is it? What's the magnitude of it? It doesn't correspond directly. Now, if I run this on the test set, I can see that the mean absolute error on the test set is about 10. All right, well, let's take a look at this. Well, first and foremost, I want to see, are these relatively close to each other? What's the magnitude? So my numbers are going from 0 to 100. That means I'm expecting to be on average 10 off if I was to launch this in the future on data that I haven't seen yet. That's kind of big considering that, as it goes from 0 to 100. Now, the other thing I want to look at are the train statistics and the test statistic. Are these relatively close to each other? I would like to see them a little bit closer. 2.5 off. Yeah. I mean, less than 3% difference. Yeah, I'll go ahead and say that's acceptable. So remember, almost always your train test statistics will be better, will be more optimistic than your test set statistics. All right. If you don't see it that way, usually you have an outlier. Next one I want to talk about is ridge regression. Ridge regression is very similar to regular regression that we've been talking about, except there is like this penalty term that prevents the coefficients from getting too big. What this does, this prevents us from overfitting. Now, why is this nice? So I personally have found myself in the position where I legally had to use models with certain predictors, but I knew that certain predictors were crap. Like, I just knew I would get a bad model if I used regular regression. And, as a professional, I don't ever want to launch a model that I know is going to be crap. If a model cannot predict well, it's a bad model. I don't care what anybody says. So what I did in that situation, I used ridge regression to get basically a better model. I wasn't really happy with it, but I was able to complete the project. Didn't have any legal issues. No one asked me questions. So the classical statistics way of approaching the situation I was in was to get rid of variables that were not useful in predictions. In fact, they were overfitting my model, and I knew I would get a crap model if I used it. What ridge regression did for me was it took those redundant predictor variables and squeezed down their coefficients so that they didn't really have much of an influence, so I could just ignore it and not worry about it, and I could sleep well at night. All right, so just like we did with regular regression, we're going to go to linear model. Now, something that's important when I do a ridge model, I need to set my alpha to a value between 0 and 1. and that helps regulate this penalty aspect. So now let's go ahead and fit it. Let's go ahead and predict on training, then test. Let's compute our mean absolute error. Now let's take a look. All right, so it's similar values. The training mean absolute error, I think, is a little bit bigger. Maybe it's, I mean, it's darn close. Yeah, it's practically the same. And the, for the test statistic, it's about the same as with regular regression. What we could do, we could play with this alpha and see if we can get something a little bit better. Let's do that. All right, so for a test, we have 9.9, that's in the worst direction. Let's go this way. 9.8, slight improvement, not much. Yeah, so they're all about the same. All right, now let's do lasso regression. Lasso regression is very similar to ridge regression. So remember that the idea with both of these is that there's a penalty going on. So basically, if I have a big coefficient in my model, remember we're thinking about linear equations from college algebra, the coefficient of the variable is what I'm talking about. If I have a big coefficient, positive or negative, in ridge or lasso, I get hit with a heavier penalty. Okay, so I don't want to be hit with a penalty. And what ridge and lasso does, it tries to find the best coefficients within that penalty. Well, what lasso does, lasso will actually start kicking out variables, while ridge will always keep them. All right, why do we like this? So ridge, remember the situation I had to legally use certain predictor variables that I didn't want to use? Well, what I did was ridge kept them in there, just kept the coefficients really, really small. So I could just practically ignore them. But when I'm legally asked, yes, they're in the model. What lasso regression does, lasso regression finds the bad predictors and will kick them out for us. So if I need to do like variable selection, I can run lasso and it does it for me automatically. So I don't have to worry about overfitting nearly as much. All right, so let's go ahead and run through this. So once again, I'm importing linear model and I have to set the alpha. Setting it to 0.05 just because it's in the middle. Let's go ahead and predict. Now let's compute our mean absolute error. Ooh, so the training error got worse, but the test set's about the same. Okay. Well, let's play around with this. Let's see if we can do a little bit better. .6 and 9.7. Oh, close. Let's try another time. Let's try with 0.9 as our alpha. 8.8 and 9.7. Okay. Interesting. Now let's do least angle regression. Now least angle regression, what it does, it takes a look at the correlation with the error terms and then tries to adjust the coefficients based off of the correlation angle. That's why it's called least angle regression, because it looks at the correlation with the residuals, then takes an angle. And in Python, this is in lasso LARS, lasso least angle regression. All right, 7.8 for my train. And then 10. Ooh, this is the worst one so far. Oh no. Let's do it again with 0.5. Let's see what happens. 8.9 and oh, it's awful. It's gonna make me cry. 10.4 and 11. Oh, the pain. It's getting worse. It's getting worse. Let's pretend I didn't do that. I'm just gonna leave it like that. All right, the next one I want to talk about is Bayesian ridge regression. All right, so if you've heard about Bayesian statistics is basically turning the idea of a parameter on its head. So it's treating the parameter, in a sense, it's treating it like a variable itself, so that the coefficient is a variable instead of being a constant. The data is treated as a constant instead of coming from a variable. It turns everything around. Bayesian statistics can be very, very powerful, but they can also take a long time to work. And if you make bad choices, you can get some really bad models. I personally have never used Bayesian statistics for prediction. I've used them plenty of times for inference, but never for prediction, just because I feel like they're not as trustworthy, because you have to make more choices. All right, let's go ahead and just run it. And everything is, I mean, sklearn makes this like, once you understand one model for coding, you know all of them. It's beautiful. It's beautiful. All right, and we got 7.8 for our train and 9.9. All right, now I want you to take a look at all of the numbers that we had for our training MAE and our test MAE. Every single time the train was about the same and the test was about the same. Well, what I really want to point out about this is that your model structure is not as important as it's made out to be. Whenever you look at videos or textbooks, online classes about machine learning, artificial intelligence, they make a big deal about different models. And I'm doing it in this class too. It's just kind of like the way it's taught. But really, it doesn't make that big of a difference. Your model structure is not as important as the data you're putting in. The data that you put in is more important. So you'll notice that what was constant with all these models was the data. And I end up getting about the same every single time. Well, whenever you're working on a project, the earlier that step is, the more important it is for getting good modeling. All right, what do I mean by that? Well, your data prep is more important than your model building. And let me go a little bit further back. Model selection is not as important as model building. Model building is not as important as your data prep. Data prep is not as important as data collection. And data collection is not as important as your experimental design. Okay, basically, like once, you can think of it as in that flow of process of designing your data collection, data prep, model building, model selection. In that flow, once you have something go wrong early at any stage, if something is not right, it propagates all the way through. So if you want good predictive modeling, you have to have good model setup before you even collect your data. So when you design what you're going to do, like that your design phase, can make or break your project, and you haven't even collected 1 point of data. And then your data collection, if there's mistakes or errors or poor measurements in your data collection, there's really not much you can do to overcome that when you get to data prep. If you have poor data prep, you will never be able to get good models out of it. So, and if you build like crappy models, then there's not really much that like model selection can do to save you. So keep that in mind. The earlier the step is in machine learning, the more important it is. It's sexy to talk about neural networks. It's sexy to talk about random forests. It's sexy to talk about support vector machines. But you know what? They're not as important as the dull, boring aspect of experimental design and data collection. Well, that's all I've got for you for now. Take care. I hope you're doing well.